Hello everyone and welcome to Infrastructure as Types. My name is Paweł Prażak and I work for Virtus Lab on the crossroads of development, security and operations. I've accumulated diverse experience over the years, but mostly writing and running JVM applications on various platforms and building platforms and infrastructures from virtual machines to enterprise service buses to cloud and Kubernetes. All of this gave me a unique perspective on common problems in IT. What are the biggest problems in IT? DNS? Typos? I personally would have to add actively misleading documentation and null pointer exceptions, especially those that show up only on production. But I'm afraid I can't solve those, not today at least. Other problems I've seen myself or my teammates struggle with the most usually come from actually implementing what has been planned and put into the backlog. Apart from functional requirements, big problems for production are reliable and fast recovery from ransomware, region downtime, and ROC employees. Accidental complexity that comes faster than expected. Advanced deployment strategies that become a requirement. Security and compliance, especially for GDPR and PCI DSS workloads, or testability and bug reproduction that become a problem. Especially creating and maintaining production environments can be fun. No one wants those calls at 3 a.m. But where did those problems come from? A lot of them come from complex business and law requirements these days. And a lot of them come from shorter and shorter release cycles and more complex architectures that makes deployment and operations effort rise exponentially. All of this result in non-deterministic behavior, operational overhead, and steep learning curve. I would summarize all of the above as increasing entropy. I've defined entropy as the tendency of all systems toward decay, disorder, and disintegration. It's not a very scientific definition, but I find it useful for thinking about systems. Entropy is all because high disorder is more probable than spontaneous order. Just like a random pile of sand is more probable than a spontaneous sandcastle. But what are the available solutions? If your problem does not require microservices, monolith might be the best option. Outsourcing operations to the lowest bidder is, in my humble opinion, never a good strategy, and it ends up costing way more than expected. Also, not everyone is Google with their planet-scale infrastructure. Be pragmatic and solve for the problem at hand. Try to simplify your functional and non-functional requirements. Sometimes less is more. If you are solving a problem that requires microservices and needs a massive scale, you can either invest tons of money and time, but do it only if your system or solution or problem is unique enough and unlikely to be commoditized. Or you can leverage the economies of scale that come with the cloud adoption. But what is cloud? Cloud is mostly a business model. You rent infrastructure or software on demand, charged by a minute or a second. What is cloud native? It's mostly a vague list of attributes your workloads needs to have to maximize the gains from using the modern cloud-like platforms. With more and more parts of the infrastructure being commoditized, there's a lot to benefit from. By adopting our workloads to cloud platforms, we can benefit from the economies of scale. We can have our return of investment faster, rather than spending millions of dollars on hardware and expertise before we can earn anything. From our point of view, the most interesting aspects of the cloud are runtime platforms and APIs. There's lots of options to choose from in terms of runtime, from just the bare metal through virtual machines, containers, programming platforms, functions, serverless, and finally, off-the-shelf software. All of this can be rented today, and more is coming to the market every year. Recently, I've even seen disaster recovery as a service, and even automation as a service, but I guess as is not a pretty acronym. More importantly, from the architecture point of view, cloud-native APIs are emerging. Great examples are Kubernetes API and Envoy Nxds API that are becoming de facto standards. We'll have a closer look at them later. How do we build an app for the cloud-native world? In general, it's all about pushing out the complexity and enabling the economies of scale that come with cloud. This requires the team to think in terms of a system of interconnected parts rather than an app in isolation. Things get more cost-effective with volume. This applies to software as well. A good example is Kubernetes. Imagine if every company had to reinvent it. Workloads need to be designed for automation. The app needs to be able to run with multiple replicas, active-active or active-passive, and be able to lose some of the replicas randomly. It needs to work well in a container with an assumption of being shut down on short notice. For example, 30 to 60 seconds for a clean shutdown. It needs to work well within the constraints of a given platform and cooperate with its orchestration and automation. In the communication layer, we can also push some of the complexity out to the infrastructure. A service mesh or an overlay network can handle, for example, load balancing, service discovery, dynamic routing, reliability and availability, encryption, traffic splitting, observability, and a lot more. A modern choice might include Google's gRPC or a service mesh like Istio. In general terms, we are dealing with computation and communication. By design or by accident, there will be a compute and communication control plane in your system, usually a combination of automation and human intervention. Here we have a simplified cloud-native system with all the major production considerations: ingress, egress, and service-to-service communication, API-driven interaction with the infrastructure, automated, observable, and secure by default, spanning multiple technology stacks and physical locations, for example, cloud, on-prem, or edge. In this example, we use them for our management and automation across the whole system. Kubernetes and Envoy here are very good building blocks if you want to automate compute and automation. I would say Kubernetes APIs is like object-oriented REST over HTTP or gRPC. It was designed to orchestrate containers, and it is used beyond Kubernetes from various operators like Prometheus operator or PostgreSQL operator to very major provider starting to wrap their proprietary APIs with it. For example, Google Config Connector. The Kubernetes itself can be run on virtual machines or bare metal. The adoption is very wide. Even VMware and IBM are providing Kubernetes-based products. On the other hand, we have Envoy Nxds API, and I would call it a typed JSON over gRPC streaming. It was designed for orchestrating network proxies, in particular, Envoy proxy, into a service mesh. Nxds API handles management of load balancing, service discovery, and other concerns. The Envoy proxy itself can be used also on the edge and mobile devices. Originally developed internally at Lyft, it is now being widely adopted by Google, Amazon, HashiCorp, and many more companies and organizations. Let's go a little deeper. Let's have a quick look at Kubernetes container orchestration. This is the core Kubernetes architecture. There is no fundamental difference between control plane nodes and worker nodes. They just run different processes. API process is the central point, backed by etc.d distributed key value store and used by all remaining components. Then there is kubecontrol, the CLI client, controller and scheduler that do all of the orchestrating, the kubelet that serves as node agent, and kubeproxy, the distributed load balancing provider. To go even deeper, kubelets work on top of container network interface and container runtime providers, for example, Calico and Docker, respectively. All internal communication is done with mutual TLS and gRPC for maximum performance and security. And as a reminder, TLS gives you a guarantee of private conversation with a complete stranger. MTLS, or mutual TLS, gives you a guarantee of a private conversation with a verified identity. And this is a layered view of the Kubernetes architecture, starting from basic hardware and virtualization, OS initialization on the bottom, to private key infrastructure and etc.d, to basic components, kubelet, CRI, CNI, API, scheduler, controller, then to add-ons, and finally, on the very top, your workloads. Okay, let's have a quick look at the Envoy Nxds for communication orchestration. Service mesh is a layer of infrastructure that workloads can use to delegate their communication needs to. It is usually a lot of proxies and at least one control plane to orchestrate it all. As I've mentioned, Nxds API is a service discovery API family built on top of gRPC that can be used to build a service mesh and more. It provides a sophisticated and very efficient communication protocol with deltas and binary transmission. It mainly handles load balancing, service discovery, secrets, and observability. It can be used to manage a service mesh, an API gateway, or a reverse proxy. The control planes can be clustered, and the whole system can scale to a massive size. The API is used mainly with Envoy proxy, but recently Nxds support was added to the gRPC itself and is being used by Google Traffic Director for proxyless mesh. I expect more libraries and proxies to follow the lead. Using Envoy proxy or any Nxds-enabled workload, we can create a complex communication with ingress load balancing, egress gateways, internal proxies, and a service mesh spanning containers, virtual machines, and bare metal, running in a cloud, on-prem, on edge, or even on mobile. It could also be possible to have multiple control planes coordinating the efforts. This is obviously a very complex scenario, but not uncommon in the large organizations. The more complexity we have, the more we want to automate. Unfortunately, automating a complex deployment strategies for a complex system might be more difficult than the system itself. There are levels to this game, but the higher levels require more experience points. From classic shell and Python scripts through Jenkins and DevOps culture to writing down everything that we can as a source code and versioning it with Git. Then there are even more levels in the works, using AI and machine learning, enabling conversational interfaces, or just completely automating a black box system that makes all decisions autonomously. Today, we'll focus on the infrastructure as code and how we can make it better. Infrastructure as code is a key component required for infrastructure automation. Any practical system involves separate computations communicating over a computer network with up to the speed of light and not faster, usually much slower. Sometimes we pretend it's not the case, until a production issue reminds us it's actually the case. If all of those systems can be defined through an API, then the whole system can be expressed in code. The actual state of the system will be eventually consistent, or even periodically consistent, with regular intervals of inconsistency between the state of the system and the definition of the system. The good news is APIs have contracts and mostly deterministic behavior, so it's possible to write a fully automated infrastructure as code in a finite time. The bad news is it's not free. I'll give you real-world examples of what are the major options of operating your systems. On one hand, we have a rather risky strategy of we'll just do it by hand. The main benefit of it is less friction at the beginning, and as a downside, the further we go, the slower we move. So huge downside and small upside in the long term. A little more sane solution is a simple scripting with popular tools. The risk-reward profile is better here, but not ideal. Both strategies can be useful as a proof of concept. Solution number 2 has downside mostly in terms of cost and time to market, and upside in reasonable levels of automation and some autonomy. In my opinion, this is one of the best risk-reward profiles for a lot of projects. It scales well up to a point. I would say about 20 teams or 100 developers. This is what I would start with for a minimum viable product in most circumstances. Solution 3 is a complete automation with very high rewards that outweigh high risk if you are willing to pay to have it built. It takes significant effort to properly develop an automatic operator for non-trivial workloads. Think twice before investing in this level of automation. A great example of a community effort to modernize legacy JVM workload is Jenkins operator, and is getting more and more automated with every release. A fantastic example of an even bigger step in automation is a custom control plane for a service mesh called Envoy Control Project. Envoy Control is a platform-agnostic control plane for service mesh based on Envoy proxy built by Polish e-commerce giant Allegro and written in Kotlin and Java. Envoy Control is responsible for feeding Envoy proxies with configurations using Nxds API based on custom metadata. They are running service mesh with 800 plus microservices across Mesos, OpenStack, and Kubernetes platforms with multiple data centers and possibly some edge. Over 10,000 Envoy proxies in total and multiple control plane instances. This is a non-trivial solution to a non-trivial problem. Not everyone needs this, but it's good to know it's possible and easier than might have been expected when leveraging cloud-native APIs and open-source software. The bottom line is there is no silver bullet. Depending on a project scope, team size, and stage of development, a different approach might be more beneficial than the other. So, to summarize what we've talked so far in one sentence, design for automation on top of commoditized infrastructure. But what could possibly go wrong? Actually, a lot. First and foremost is unexpected complexity. Then come problems with diagnostics and testing. when non-deterministic behavior emerges. Abstraction layers, leaking left and right, integration problems, especially around networking and storage. Then there's the steep learning curve, all the APIs, all the containers, virtual networks, multi-layered load balancing, and so on and so forth. Finally, there's a loss of control and familiarity with a new and unintegrated toolchain. Even DNS becomes even more of a problem than usual because of in-cluster and out-of-cluster DNS differences. Also, JSON and heavy YAML platforms are very typo-prone. From that list, I believe we can address accidental complexity, learning curve, loss of control, and typos to an extent. Let's have a quick look of what it takes to run a workload on Kubernetes. Tutorials and demos would have you believe that it's just those two resources, deployment and service. This is actually what it takes to properly configure a workload to run on production on Kubernetes. But that's not all. There are references between most of those in text with no easy way to check them. Crazy, isn't it? And that's just for one microservice. So multiply everything you see by at least 10 for any practical system. And now imagine there's a typo somewhere in one of those YAMLs, and you need to find it at 3 a.m. because the prod is down. To minimize the downtime at the cost of even more complexity, then people introduce various deployment strategies. From the very simplest fixed strategy, when a version A is terminated, then version B is rolled out, classic, to rolling update. Version B is slowly rolled out and replacing version A, to blue-green deployment. When version B is released alongside version A, then the traffic is switched to version B. Then there's canary deployment. Version A is released to a subset of users, then proceed to a full rollout. Then there's A/B testing. Version B is released to a subset of users under specific conditions. And there's shadow deployment. Version B receives real-world traffic alongside version A, and it doesn't impact the response. For every strategy other than fixed strategy, the workload needs to be well-behaved under automation. At least it needs graceful termination and readiness probe. This is the simplest blue-green deployment using only Kubernetes, and this is only the happy path. In my opinion, being able to use strongly typed general-purpose programming language is a game changer. Real-world use cases come with complexity that YAMLs and JSONs can't reliably express. With infrastructure as types, we want to make every Scala developer feel at home in a cloud-native environment, starting with a Kubernetes-specific proof of concept. We believe that developer-friendly infrastructure abstractions and interfaces are increasingly necessary in the age of the cloud. We'd like you to be able to define in Scala a significant portion of your system, if not all of it. We want to enable Scala developers to be able to write anything from simple scripts to very complex automation, like a custom service mesh plane in Scala, by giving you a flexible toolset. There are 5 rules we stick to. Enable easy to read and maintain user code. 80% of use cases should be easy and straightforward to express with high to mid-level abstractions. Provide extension points for the remaining 20% of the use cases with some low-level abstractions. No unnecessary abstractions, and a balance between type safety and type magic. This is an example of two microservices in an ingress. First, we define high-level basics, a Kubernetes namespace to hold our resources in, two applications for our microservices, and one gateway for a traffic ingress. All of these definitions will be interpreted to Kubernetes resources later. Then we can add some optional details using functions that will manipulate the interpreted Kubernetes resources directly. Here we configure number of replicas and Google Cloud specific ingress settings, including a managed TLS certificate. And at the end, we bring everything together. Interpretation takes our high-level definitions and produces Kubernetes API-specific data structures. Next, we use the details functions to customize the Kubernetes API-specific data structures generated in the previous step. Then we select all those data structures using Kubernetes API to have them applied. And finally, once cluster applies the changes, we interpret the results using, again, Kubernetes API. Here we have two custom detail functions used for Google Cloud specific settings regarding ingress. As you can see, we mostly add annotations to existing resources in this case. And there's the beginning of custom resource definition. And we use a custom resource definition to configure a Google Cloud managed TLS certificate. We've used it already in the previous slides. Basically, we defined a data structure for the REST request, and this Kuber library underneath does the rest. And these are the resources that will be applied to the cluster. These are the YAMLs representing them. And here we have generated two services, two deployments, one ingress, and one managed certificate, all linked automatically with correct labels. So it's basically a hello world with two microservices and a TLS-enabled ingress. With this bare bones proof of concept focused only on Kubernetes, we were able to solve some problems already. Sorry. The error-prone text-based references between YAMLs are now handled automatically, eliminating a whole class of problems with typos and mislabeling. Also, with good defaults and examples, we are able to make the learning curve less steep. Familiar tools and programming languages lower some of the barriers to entry. By using a general programming language, we were able to leverage all of the complexity management and refactoring abilities of the language. We were able also to test a derivation of network policies rules from high-level connectivity graph, so it's possible. We believe that with more work, we could be able to do even more, especially with orchestrating Kubernetes and a service mesh. We have lots of ideas for the future development. The main idea is to go forward with another iteration of the APIs and implementation, taking advantage of Scala 3 unique features. We also already see areas for improvement in current abstractions to make them even easier to use. Basically, sky's the limit. low-level libraries, deployment strategies, test frameworks, service meshes, serverless, SBT, Ammonite integration, and even other programming languages. Unfortunately, I can't promise anything. It's still very early in the development lifecycle, and we are still exploring both the solution space and the problem space. To prioritize our effort, please feel free to give us feedback as to what do you think we should do next. You can reach out to me on Twitter or fill a very short anonymous form. Thank you, and big shout out to Łukasz Biały and all my colleagues for all the help.